This is a video lesson for Introduction to Momentum. The learning target for this lesson is, I am learning to describe the linear momentum of an object or system. The success criteria for this lesson are, I can define an object's linear momentum by its equation, and I can understand that linear momentum is a vector quantity and has the same direction as the velocity. So in general, when we talk about linear momentum, or just momentum in general, we're talking about momentum in a straight line as opposed to momentum which is curved, which we would call angular momentum. So if I say momentum, I mean momentum which is going in a straight line as opposed to angular momentum. So before I start this video, this is my favorite momentum video. So a little bit of preface of this about this video. So this video is it's set in England, and this is a town that came out to build this giant snowball. They are they're thrilled that it's snowing. It hasn't snowed in this town a whole lot in a really long time, and so everybody came out to build this giant snowball because they're all thrilled that it's been snowing after a long time since it snowed. So my favorite part of the video is when the guy jumps on top of the snowball and he almost gets rolled over. I love that part. I feel like you really want to see the guy get squished and come up on top of the snowball like in a cartoon. Of course, I don't want anybody to get hurt, but I love that part. So I love that video because it's a really good demonstration of momentum. You see this really giant snowball picking up speed as it rolls down the hill. So momentum is really just about the speed of an object and its mass. So the motion of an object. So it's like putting a mathematical amount to the motion of an object. So the larger an object, the more massive an object is, the more momentum it has, and the faster it's going. So the more velocity an object has, the more momentum it has. And we'll get into that as we go through this lesson. Okay, so how do we think about momentum? So the equation for momentum is P is equal to M times V. So P for momentum, we used up all the M's for mass, and capital M is molarity in chemistry. So we had to use a P for momentum. So P is equal to M times V. So M is the mass of the object and V is the velocity. So the units for momentum are kilograms times meters per second. And we think of this also in terms of Newton seconds. So newtons times seconds is equivalent to kilograms times meters per second. So we can think of this as the quantity of motion of a moving body, or how hard it is to stop a moving body. So this is kind of like the mathematical version of inertia. So in modern physics, we think about how strongly an object can interact with or exert a force on another object. So for an example, we think about a heavier, faster car interacts more strongly with another car when they collide. Or in subatomic particles, so in particle physics, subatomic particles interact with each other as exchanges of momentum. And that's really how particle physicists think about the collisions between particles or subatomic particles. So protons and neutrons and electrons slamming into each other. They think about those in terms of changes or exchanges of momentum. So momentum is a vector quantity, meaning it's important to know not just the magnitude of the momentum, but the direction that the object is moving in. So positive is in a rightward direction, and negative is in the leftward direction. So the motion of the object If it's in the rightward direction, it's going to be a positive momentum, and if it's in the leftward direction, it's going to be a negative momentum. And this is based on the velocity. So which direction is the velocity going in? Okay, so let's talk just a minute about conservation of momentum. So we'll get into more detail about conservation of momentum as we move forward, but I just wanted to put this in here just as a quick example. So momentum is a conserved quantity. So just like energy, momentum is conserved. So the total momentum before a collision is the same as the total momentum after a collision. So you can think about two billiard balls, two pool balls. So if the balls are moving towards each other, they each have a mass. The mass is the same for billiard balls. So each one is moving toward each other. They each have a velocity. So they each have momentum. And so when they collide with each other, they're each going to move in a different direction. So after the collision, they both have a new. Each one has a new momentum. They have momenta, and so you can calculate the momentum that each one has before the collision, and you can calculate the momentum that they have after the collision. And if you add up the momentum that each one has before the collision, and you add up the momentum that each one has after the collision, the sum of those momenta will be the same. This is assuming that there's no outside forces acting, which of course on a pool table there's friction. But if in a perfect world, the conservation would be the addition of the momenta prior to collision and the momenta after the collision would be exactly the same. So here's our equation for the conservation of momentum. So we have the mass of object 1 times the initial velocity of object 1 plus the mass of object 2 times the initial velocity of object 2 is equal to the mass of object 1 times the final velocity of object 2 plus the mass of object 2 times the final velocity of object 2.
Okay, let's look at a couple of examples. So example number 1, we've got a 905 kilogram compact car. It's moving eastward at 26.6 meters per second. So eastward is to the right. So we want to figure out the momentum of the car. So momentum is equal to mass times velocity. So the mass is 905 kilograms. The velocity is 26.6 meters per second. So multiply those together. That gives us a velocity of 24,073 kilogram meters per second, or we can call this also Newton seconds, and that is eastward. Okay, so let's look at the second question. Determine the speed of a 2,140 kilogram van that has the same amount of momentum. Okay, so we're trying to figure out the velocity of the van. It has the same amount of momentum. So if we look at our momentum equation, we're looking for velocity. So if we solve this equation for velocity, velocity is equal to momentum over the mass. So we're given the momentum from the first question. So our momentum is 24,073 kilogram meters per second. Divide that by the mass of the van, 2,140 kilograms. Kilograms divide out, and we have a velocity of 11.25 meters per second. Okay, example number 2. A cart carrying a block moves to the right with constant speed. The block does not slip on the cart. Consider two systems. System 1 consists only of the block, and System 2 consists of the block and the cart. Which of the following correctly compares the speeds v1 and v2 of System 1 and System 2, and the magnitudes of the momenta p1 and p2 of the systems respectively? Alright, so we have system 1 and system 2. We have velocity 1 and velocity 2 and momentum 1 and momentum 2. So if we're talking about the speeds, so velocity 1 and velocity 2, well, the cart and the block are moving at the same speed because the block is sitting on the cart and the block is not slipping, so they have to be moving with the same speed. Okay, and then we want to look at the momentum. So if we think about our equation for momentum, we have P is equal to M times V. So if they're moving with the same velocity, whichever system has the greater mass is going to have the greater momentum. And since the system 2 has the cart and the block, this system 2 has the greater mass, so momentum 2, or system 2 has a greater momentum. So we have system 2 having equal velocity and greater momentum, so the correct answer is C.
Okay, so what did we learn in this lesson? We learned about momentum. So how hard it is to stop an object in motion. That's the basic idea about what momentum is. So the equation for momentum is P is equal to M times V. And it's important to remember that momentum is a vector. So its direction is the same as the velocity. So momentum has both direction as well as size, or as well as magnitude. All right, thanks everybody.